And let me get my... Okay. Let's get rolling. We're going to be talking about surface temperature today and how an astronomer measures the temperature of the surface of a star possibly millions of light years distant. And the way that we do it is by looking at the color of the star. So, for instance, Betelgeuse is red. Those of you that went to the observatory last night, raise your hand if you went to the observatory, by the way. Very nice. Good. Okay. One of these stars that you looked at was Albireo. And I mean, if you were there, I think there was a smorgasbord of things to observe. One of them was Albireo. And if you look at it with your naked eye, it looks like a star. It's the star at the head of the swan in Cygnus, the swan. Summertime constellation flying down the Milky Way. And the head of it, or the beak, or the eye, or whatever you want to call it, at the end of the long neck, is Albireo. And one of them is kind of orangey yellow. That's this one. And you can't make them out separately unless you look at it in a fairly good telescope. You know, you don't have to go to the Hubble Space Telescope, but you know it has to be a fairly good one. And if you do, it'll look. Now take a look at this. Look at the color. All right. Now that's going to be important for us today. All right. And you can look up, buku pictures of Albireo, Chenille, on, the internets. So the other one is bluish. And let me go back up here to this one. This is Albireo A. So go ahead and make a note. It's a double star. And actually, Albireo A, the orangey one, is a giant star. It has 5 times the mass of the SUN. All right? And as I've mentioned before, I believe in this section, the mass of a star, whether it's 5 times the mass of the sun or 0.5 times the mass of the sun, we have stars that are smaller. If you know the mass of the star, it's like knowing the DNA. And a little baby before it's born, its DNA is set. So theoretically, you know how tall it's going to be when it's an adult. Within an inch or so. Its hair color, eye color, fingerprint. All the stuff. That is set by the genes, the genetic code. Whether it's going to be allergic to what do you call that stuff? Lactose intolerant. They don't have a gene for digesting lactose. All that kind of stuff, set before, before they're born even. And then they're born, and then you find out about all that stuff. And that's for a star, it's much simpler. For a human, even a little teeny baby, this enormous DNA molecule for your genes, and there's several genes. And those things encode enormous amounts of information, but for the star, it's just one item of information, the mass. If you know the mass, you know how big it's going to be when it is born as a star. You know how long it's going to live. You know its end state, whether it's going to be a white dwarf or a supernova or something in between. All right, so the mass of this one, orangey, amber-colored Albireo A, it's a giant star, and it is 5 times the mass of the SUN. How do we get the mass? It's close enough that we can get a parallax. Obviously, we can resolve them, So you get a parallax, figure out a distance, figure out the semi-major axis and all that stuff, use Kepler's third law, get the mass. Because we can also do the same thing for Albireo B. Now, Albireo B is the blue one. B for blue, it's the second brightest, so that's why it gets the letter B, but it also happens to be blue. It is a white dwarf. Now, it's a dwarf, and it's a star that's born and it's now in retirement. It's long since. And the mass of the Albireo B is 3.3 times the mass of the sun. We normally rate the mass of stars in multiples or fractions of the mass of the sun. So for this one, it's 3.3. All right? And it's blue. Bluish white. So, what we're going to find is that examining this and knowing its distance fairly well, we can actually figure out its absolute luminosity. So we know that it's not a giant star. I mean, there are blue giants, blue supergiants, but this is not one of them. This is a white dwarf, bluish white dwarf, we call it. And Albireo A actually is a gigantic star, and we're going to be talking about that. And so, as I mentioned, today's main topic is really looking at the surface temperature or trying to measure the surface temperature of a star based on its eyeball color. And for these two, one of them has an eyeball color of orange, and one of them has an eyeball color of kind of bluish white. So that tells you, in everyday parlance, about the temperature, at least of the surface. Now, I want to reinforce some stuff that we talked about last time. Specifically, this particular diagram we talked about, a Dopplergram for the SUN, and I want to reinforce something I was a little bit unsure of. I made sure I double-checked it. I was right. The positive numbers, where it's whitish and almost orangey, that corresponds to a positive velocity, and that means in the astronomer's scheme of things that the velocity is away from the observer. All right? So this half of the sun on the right, let me get my cursor over here. This half of the sun over here on the right is that part's moving away from the astronomer. It's moving away from the observer. Now over here, if you have a dark area, this scale down here, -2 kilometers per second, that's the black end of this color bar, that means it's actually moving toward you. All right? So a negative velocity means toward you. Now, if you see something that's moving towards you on the right and away from you on the left, means, it's moving away from you on the right and towards you on the left, that means it's spinning. And so what we deduce from that, go ahead and sketch in your notes, an arrow, and try to distinguish it from the others, in the sense of spinning. So this one's it's spinning from left to right across the front. And in the back of the star where we can't see it, it's going right to left, of course. All right? And so here's your basic logic. This is what I want to reinforce with you. So you scan the surface of the star or the planet, whatever it is you're looking at, or the car. You know, the police officer's got a radar gun, and he scans one point on your car, and he looks for a Doppler shift. Okay, so you scan it. You know, in this diagram, the scan is very, very small pixels of the sun. You know, very, very small areas of the sun. So you get a lot of scans, and we measure a lot of Doppler shifts, but they do organize left and right. And so you get that, and then you calculate the velocities from the Doppler shift. So the stuff over here that's moving away, that's a little bit, if you were to look at hydrogen alpha, for instance, you would see that hydrogen alpha on the right is a little bit redder than 656 nanometers. So it might be 657, 657.3 or something like that. Now over here on the left, the stuff that's coming towards you, that's going to blue shift. Okay, so that might not, it won't be 656. That's what we would see in the lab. So you'll see something over here, like maybe 655.2 or something like that. Right, a little bit smaller wavelength. But then right here in the middle, where you have 0, that's kind of the orange area of this chart. Right in here, you don't have any, it's not really, it's moving left to right. It's not moving towards you, it's not moving away from you, it's going straight to the side. Right there in the very middle of the disk. Okay, so you don't have any Doppler shift. At that, the scans that you put on that region of the SUN, they're going to come back straight 656 nanometers for H alpha. And you can do it with other spectral lines, like the bright yellow one from helium, or maybe neon. You want to study neon. You can use neon's spectral lines as well. So rotation. The other thing is you can even use it to look at these convection cells. Now we did talk about this. I will want to reinforce this is figure 5 in chapter 15.1. So in case you want to study and read, yep, right in there. That's a sunspot up here in the second image, upper left corner. And the dark color is, it's still pretty hot. It's not like it's totally not emitting light, but everything else is so bright around it from heat, from a slightly higher temperature, that it looks black or dim. All right, so these images like this also tell us about the temperature. So we look at these cells, we do a scan, we can see that the stuff in the middle is coming up toward us. It's got a slight blue shift, and the stuff around the darker edges is moving away. The color, so that means it's dipping back down into the convection zone of the sun, and those are convection. That's how we know that these are convection cells. And we can also judge the temperature by looking at the brightness or the color. We talked about this one last time. The structure of these of the photosphere is called granulation. These structures, anyways. The granules are typically 700 to 1,000 kilometers in diameter. So, in other words, the width of Texas. Now, for us, Texas is ginormous. I drove out to Austin in the summer, and you drive through. You know what's a long drive is from Orlando to get out of the States. So I drove from Orlando up to Lake City, turned left on Interstate 10 through Tallahassee. That was like hours, and I wasn't even close to being out of the state. But finally, I passed Pensacola, and then I was in Alabama, all right, and then Mississippi. And then we dipped up we dipped north, so we went through Baton Rouge, so we didn't go through New Orleans because there was a hurricane coming. So we dipped up to the north through Baton Rouge, and then dipped back down into Houston. And so you go up to Baton Rouge, and then you dip down, and so you cross the border, the Texas-Louisiana border, right? And all of a sudden, all the mile markers change, because you're at the end of the state. You're in a new state. And I'm looking at the mile markers, and, the exit numbers are the same, So it was like 780 or something, that very first one. And I thought, oh, my God, 780 miles just across Texas. That's worse than Montana. It's worse than Florida. It's worse than Montana. Anyways, we only had to drive to Austin, but it was amazing. So these things, they seem small on the sun, but they'd be big to us, the size of Texas. But we have weather systems that are big. Like Harvey was supposed to be a pretty big storm, as I recall. Big and wide. I don't know if it was the same width as Texas, but a good fraction of Texas. So we have weather systems that are that big, and you have smaller convection systems in your kitchen. Anytime you boil some water and let it go to a rolling boil, you're getting a convection cell the size and shape of your kettle. So another thing that I mentioned last time, and I want to mention it again, the typical point in the photosphere, the pressure is less than 10% of Earth's pressure at sea level. So in other words, like the air pressure here in Orlando, we're pretty much sea level. And the density is about 1/10,000th of Earth's atmospheric density at sea level. So we would have if it was our atmosphere, but at those densities and pressures, we would have a really hard time breathing. All right, and it's similar. You go to and go ahead and write down in your notes Mount Kilimanjaro in Africa. In East Africa, there's snow up on top of that. It's near the equator, but they still have snow up there. Throughout large parts of the year. And Mount Kilimanjaro, I don't know, it's like 18,000 feet. You could look it up. But Mount Kilimanjaro is about the dividing point. Half of Earth's atmosphere is above that, and half of Earth's atmosphere is below that. And when you get up there to 17,000 feet, 18,000, 19,000 feet, you are starting to become oxygen starved, and you have to start thinking about using oxygen. And when you're up there on Mount Everest, their base camp is pretty close to that elevation. And then they go more, another 15,000 feet up from there. Oh my goodness. But there are guys that don't use oxygen to get to the top of Mount Everest. They climb, without using oxygen. And you have to be super in shape to do that. And you have to be foolish too, because it definitely shortens your life if you do that. That's why they call it the death zone. Up above 15,000 feet, it's a little shaky to go that high because of the pressure conditions. All right. Here's another pull quote from chapter 15. The solar photosphere, where the density of atoms is sufficiently low, the photons can finally escape from the sun without colliding with another atom or ion. Now that's actually important for us at the end of the semester as well, because in the early universe, a few minutes after, or a few 100,000 years after the Big Bang, we find another thermodynamic condition similar to this, that the density and the pressure of of all the matter in the universe was cooled down enough so that now photons could stream freely without having, one more bang into an electron, one more bang into a proton or a deuterium nucleus, one more bang into a helium nucleus, and then that's it. The next destination, planet Earth, or Mars, or any other planet, or Alpha, some space alien in Alpha Centauri. Every ray of sunlight's heading somewhere. If it gets to the surface of the photosphere is now so sparse, low pressure, that you're going to have your last collision. And because photons of light make physical electromagnetic, go ahead and make a note of this. Photons of light make fundamental physical interaction electromagnetically with charged particles, electrons and protons. So a nucleus, or one of the electrons going around the nucleus. So a photon will interact, change its velocity, changes the direction of its motion. It's still going at the speed of light, maybe surrender some energy by interacting with an electron or a proton or some other charged nucleus, wherever they are found, whether it's in the surface of the sun or in the radiation zone. And that's basically why the radiation zone, it takes forever for a photon to be created in the nuclear reaction in the core, and then zip, zap, ricochet around for a few 100,000 years, and eventually get out to the surface where it can stream freely at that point out to Earth. But it eventually will do that. All right. Now, another thing I want to emphasize with you in terms of convection is Betelgeuse. We can actually see convection cells on Betelgeuse, and this projector is rendering that image fairly well. You can see that some of it is brighter, almost white in color, and others are deeper towards the red. Now, I believe this is a false color infrared image of Betelgeuse, and it is a big star. It's a supergiant, and it's fairly close to Earth, so we can actually make out surface features. Now they're still pretty big. It's not like the close detail we have for the surface of the sun. But yeah, we can see these big convection cells. All right. So we like to know about convection, and we like to know about Doppler shift and all that kind of stuff. Doppler shift also helps out in other ways. Not just looking at Betelgeuse, not just looking at the sun, but exoplanets as well. So go ahead and make a note here to yourself. Exoplanets, yeah, we can find planets on other solar systems far away from us that we know are planets. And here's the very most famous one, 51 Pegasi b. B means the second object in that star system. 51 Pegasi A, you normally don't write that. That would be the star itself. Okay, so what we do is we look at the Doppler shift in the star, and we see if there's any variations over time. And if the variations repeat, that means something is causing the star to move away, move toward, move away, move toward, move away, move toward, move away from Earth, move toward the Earth, move away from Earth, move toward the Earth, back and forth. And that's what we found with 51 Pegasi. It's H alpha line, or maybe one of the helium lines. They were looking at it and they realized, dude, we're getting a Doppler shift. We're getting a blue shift and then a red shift and then a blue shift and then a red shift. Not great shakes, but we're getting it. We can measure it. Something is causing the star to move slightly toward Earth, away from Earth, toward Earth, away from Earth. And here's a nice pull quote from a NASA website. I'm going to give you the web address for it. 51 Pegasi b was detected using the radial velocity method. In other words, Doppler shift, looking for the radial velocity toward, away from Earth, which involves a very carefully measuring the changes in the spectra of the host star. So in other words, looking at, like that bright yellow line for helium, and looking for a blue shift, and then a red shift, and then a blue shift, and then a red shift on the same periodic basis. And if you get that, then what you know is, or the H alpha, red shift, blue shift, 657, 653, 657, 653, 657, 653. You getting the pattern? That's a blue shift and a red. And if you see that, and it's always the same period of time, that means you got a planet that's orbiting. And here's the artist's conception of the planet. 51 Pegasi b is a little bit bigger than Jupiter, so they made it look a little like Jupiter. It's way closer, though. It's way close in. Thomas. Sometimes we do. Yeah, that's direct measurement, direct observation. Yeah, we could. Yeah, some of our big telescopes, like in Hawaii and South America, they've spotted some directly. Yeah, in the glare. Yeah, yeah. But this one is what you would call spectroscopic detection from the Doppler shift. 657, 653, 657, 653. You want me to keep going with that? So that would be called spectroscopic detection. Doppler shift.
Wondering, like, when people say that or when scientists say that there's planets that can inhabit life or have water or right glass.
Dude, it's amazing how much information they can get from this. And I got a data plot here for you, and it's kind of cool. Here's the star. This is the artist's conception of 51 Pegasi, the star itself, the host star. All right. Now, here's the website that I want you to jot down. It's a nifty little page, a little blurb about 51 Pegasi b and why it's how it was found and who the scientists were that found it and stuff. And I don't know if you can look it up in terms of, 657, 653, 657, 650, but you might be able to, look that up somewhere. And so it'll give you, it's a nice blurb sheet, and it can get you started on the hunt for 657, 653. Yeah, Desiree.
Okay, so for the Doppler shift, so it's either you can like spot a planet like through the telescope directly, or you can spot it through the electromagnetic field.
Yeah, and some of the other things, here's another way that we've also been able to spot them. The star blots out, the planet goes in front of the star. And the star dims out just a teeny bit. And if you have a good telescope and a good light meter, you can measure what we call the light curve. And if the light curve dips periodically, so instead of going 657, 653 redshift, blue shift, if it goes dim, bright, dim, bright, dim, bright on a periodic basis, then that means we have an eclipsing system. Okay, so that is not direct detection either. Because we can't break out the star itself. But if you time it right, if you know the distance and the size of the star and stuff, you can figure out how big the planet is. It's amazing the stuff that they can dig out. Go ahead, question.
Yeah, you said that the detection of the spectra takes place very quickly, but doesn't an orbit around a star or another planet take hundreds of years, depending on the distance? How do we quickly check that shift?
Well, if it was hundreds of years, we would have a hard time measuring it. But look at this one. There it is. There's the velocity curve. All right, now look at the period up there. Capital P, 4.231 days. So yeah, they just got to look at it for a couple weeks. And bang. So they're seeing 657, 653 for a couple weeks. And then they convert all those blue shifts and red shifts into a speed away and toward, positive. And this one, the maximum speed plus or minus is about 56.04 meters per second. So it's not really rattling 51 Pegasi very much. But the term that astronomers frequently use is wobble. When we see this, we know that all the hydrogen and helium are getting shuttled back and forth. Not very big, not very bigly. But yeah, 56 meters per second. That's like 100-something miles an hour, max. So you get 100, so you get, a red shift and a blue shift, 100 miles, 100-something miles per hour towards you, 100-something miles per hour away from you, and then back and forth. And what they do is they just map it out. And this is actually all their data folded into one diagram. This is called from 0 to 1.0 in the phase or the cycle of the actual observations. So they figured out, it's about a 4.231 day cycle. And Kayla, that is very fast. That means that this star is very close, this planet, this exoplanet, it's very close. Notice that they have an eccentricity up there as well. So yeah, you can analyze this curve and you'll know that its eccentricity of the ellipse is about 0.014. You know, Kepler would have caught that, you know, and we easily catch it. Now, the complication in all of this is, what if the orbit is tilted with respect to Earth? And what if it's tilted away from, you know, like, so so here's this folder, right? So if this is the orbital plane of the planet and you're looking straight into it, you'll catch maximum Doppler shift on either side of the either side of the thing. But what if the orbit is tilted like this? All right, then you're not going to get maximum. Or what if it's tilted? So it's in 3 dimensions. But we have ways to figure that out. It's like doing ginormous amounts of trig and making a lot of observations. And hopefully not over the course of centuries. But, Sirius B has a period measured in decades. And so, we do watch stuff for decades. So far, I don't think we've measured stuff for hundreds of years. But we eventually will have data for hundreds of years. But this one, just a few days. So, now, I want to go and talk about surface temperature. And this guy, Max Planck, who was a brilliant German physicist about a century ago, 110 years ago, he's the one that figured out that put all this science together that we're about to look at. All right. Now, make a note, figure 3, and actually this is in section 5.2. We're dipping back for a little bit into chapter 5.2 to understand these spectra. Now, this one's a little bit different. This figure 3 here, and we'll look at a bigger version of it in a few minutes. I'll just magnify it for you. It shows the relative brightness at all kinds of different wavelengths. Now, it doesn't go all the way down to 0, but it goes to very small wavelengths here. And that's ultraviolet. Go ahead and make a note. Ultraviolet is short wavelength. Infrared, it measures intensity all the way out here, or it maps out intensity all the way out here at really long wavelengths. And this scale, the horizontal scale, is nanometers. 3,000 nanometers is way out here at the far right. All right, now that's infrared, long wavelength. All right, and some people would even call this microwave. All right, one man's microwave is another man's infrared. In the middle is Roy G. Biv, visible, between ultraviolet and infrared. Now make a note. This is not on the slide, but make a note. The wavelength range for visible light is 400 nanometers to 700 nanometers. All right, now H alpha is a beautiful red, 656 nanometers. All right, so the red end is 700 nanometers, and the blue end is 400. And you can kind of see that right here. They've got the violet end of Roy G. Biv. So on this graph, Roy G. Biv is backwards. It's VIBGYOR. R is over here on the right, but it's at 700 nanometers. And they've got violet down here a little bit past 400. That's all right. And just as a side note, 400 for violet, 700 for red, for the deepest red, is approximate. So you might have, depending on your eyeball, the retina of your eye and stuff like that, you might pick up a little bit into the infrared. So you might pick up 705 nanometers. So make a note of that. Some individuals might pick up even deeper into the reds than 700, so like 705. And we know that bees and different animals and stuff do see into the infrared. All right? Now, at the other end, it's possible too that you can see a purple even deeper than the deepest purple. In other words, it might be that you can see, or a friend can see 392 nanometers. So it's not like a hard limit. It's just an approximate 400, 700 nanometers. And we know that some animals can definitely see above 700 nanometers into the infrared. All right. Now this graph shows on the vertical scale the relative intensity. All right. And it's in arbitrary units. We're not really mapping out the units on the vertical scale. We are on the horizontal scale. Now, I want to relate this graph, and we're going to be talking about this graph for the rest of the class. I want to relate it to some everyday experiences that you know from common sense, hopefully. If you ever go into the kitchen and you boil some water for a cup of tea, you turn it on high. And the stove element gets red hot, you're ready to go. Toasters, the same. Toasters heat up really fast because they have much smaller wires. But that on the stovetop, that little spiral thing, it takes a while to heat up, but it definitely gets hot. And when that thing's red hot, then you got a lot of... But by the same token, go ahead and make a note of this. Before it gets red hot, it's just kind of grayish color. Kind of a dark gray. But if you put your hand near it, you can feel the warmth. It is warm. It's just not red hot. And that brings up the second one. If something gets white hot, it's even hotter than red hot. Now that's why we call that star Albireo B a white dwarf. The surface is really hot because it's whitish blue. And so, for instance, if you try to boil a pot of water with a white hot stove element, and I've never seen a stove that does that, but I mean, probably, NASA could probably build one. And if they build one that gets white hot, it's taking a lot of juice and it's going to boil water super fast, okay, because it's hotter. Now that's related to this diagram that we have over here to the side. And we use this diagram, figure 3, especially when we're trying to study stars and other large objects that are incandescent, because they have similar effects. So what we're going to be talking about, and we actually have some equations for stars, you could actually use in the kitchen. You don't go around trying to calculate the surface temperature of your kitchen element, but you could if you wanted to. Use the same thing. Now, the first law, the first concept that we're going to apply to stars is something called Wien's law, or Wien's law. That's the German pronunciation. And basically, it tells you, it relates the color of an object and its temperature. So just saying that something's red hot or it's not red hot, that's nice in the lunchroom when you're just talking about stuff. But if you actually want to get a number, you have to use Wien's law. And it's nice. It works good. The other one is the Stefan-Boltzmann law, and that relates to the luminosity, the watts per square meter from every square meter of incandescent object that you're trying to study. All right, whether it's a star or something else. All right. Now, let's talk about Wien's law. So just jot down Wien's law, Stefan-Boltzmann. We're going to go into detail with Wien's law now. All right, so here we go. Let's look at this thing up close. Here it is. All right, and as I mentioned, we've already taken a look at it, but now I want to take a closer look at it. There are 4 different plots. The big one marked 6,000 Kelvin. Go ahead and make a sketch of that one. All right? Map out your horizontal axis and make this one tallest and sharpest. And then the next one down, this kind of greenish one here, nest that one underneath, and the peak of this second one is not quite as sharp, and it's a little bit to the right. All right, now we're going to look at those two, we're going to close up again. Here's the peak. The first one, the 6,000 Kelvin curve. The peak color is approximately kind of greenish yellow. All right? Right in the middle of the Roy G. Biv. But now the 5,000 Kelvin, the peak color is shifted a little bit to the right, and it's right in the extreme reds. So that might be fairly close to 656. You know, the same wavelength as, but it's thermodynamically controlled. It's not a quantum phase transition like 656 nanometers. But you know, you can get something to have a peak right at that temperature if you want. All right? Now, here's the major concept. All right, here's the big picture again. The maximum wavelength, in other words, the wavelength at which your object is brightest, okay, it's the greenish yellow for 6,000. For slightly cooler, it's red. That wavelength gets longer as the temperature decreases. So look right here. 4,000, another 1,000 Kelvin cooler. Now, nest this curve. It's shorter, so it's not going to give you as bad sunburn. You know, 6,000 Kelvin object is going to really blaze you up, okay, because it's putting out a lot of joules per square meter per second. Right? But this one down here, 4,000, it's going to be hot, but not nearly as hot. So it's nested below the other two, and it's shifted the peak. Make sure the peak is rounded even more and slightly to the right. Now, if you look at the peak here, it's about 9,000, or not 9,900, all right? So, or 800 something probably. All right, and we're going to calculate this in a minute. Get your calculator out, by the way. And your clicker. We're going to do a clicker question in just a second. And then this idea that the max wavelength gets bigger and bigger, it shifts or it displaces to the right with temperature. And it nests into a shorter or not as bodacious of a curve. Here's the last one in this diagram, 3,000 Kelvin. It's just right down there. All right? So this is what happens when you measure the intensity. So you take a light meter and you send the object, the light from the object, into a diffraction grating. It spreads out into a rainbow. You measure the intensity at each color of the rainbow, and you get a curve like each of these four. And if you do it carefully, 6,000 is going to be your tallest curve. It's going to have a lot of voltage from your photometer, your light meter. And 3,000 is going to be kind of pokey. You're going to get some measurements, but it's going to nest underneath the other three. Now, the mathematical formula for that is this. This is the Wien displacement law, they call it. The maximum lambda in nanometers is 3 times 10 to the 6 nanometer Kelvin. That's the numerator. That's a constant of nature. Divided by the temperature in Kelvin. All right? And so if you take 6,000 or take 5,000 or 4,000, you put that in the denominator, and then you do your math, you'll get a bunch of nanometers. And that nanometer number will be the exact wavelength of your peak. You know, whether it's here in the G's, here in the reds for 5,000, and in the infrareds for 4,000 and 3,000. Oh, by the way, remember what the surface temperature or what the Kelvin temperature is for humans? 98.6 Fahrenheit. Remember we did that Tuesday? What do your notes say? Anybody write, what did your notes say? 310. Right? So 310 would be even pokier. It probably wouldn't even look like much of a curve. It just looked like a little, a line with maybe a little bit of a rise. But the peak of it would be to the right of 3,000. And the reason that that's important is because, like all these army men that go around in, night vision goggles, they're trying to find guys out in the desert, out in the forest at night, and they're looking at the peak wavelength for 310 Kelvin, which is infrared. It's a very specific wavelength. So those vision goggles, they won't see they're not going to pick up all values of infrared. And they make a false color display at a very specific wavelength band for human beings. Because, when it gets cool out at night in the desert, sometimes it gets really cold out there in the desert. But you're still at 98.6. So the desert is going to be, like maybe 280, and you're going to be at 310. So if you have detector for 310 that blocks out 280 or diminishes 280 wavelength, you're going to see people and not so much of the background. So that's how night vision goggles work. Now I'm going to give you a calculation here, and this is multiple choice. Here's your question, and we're going to use this equation, and we'll go through it step by step afterwards. Go ahead and give this one a shot. 3 times 10 to the 6 in the numerator, that's the same as 3, 0, 0, 0, 0, 0, 0, 0. So if you're on a calculator, you can do that. And give me the peak wavelength of this list, A, B, C, and D, in nanometers for a 5,000 Kelvin object. Now this is cooler than the sun. This is the second curve in figure 3. And so take a minute to do that. And this one, it should be fairly easy to do on pencil and paper if you don't have your calculator. But yeah, definitely start bringing your calculator. So go ahead and vote. One more time. And you can talk to your neighbor and stuff if you want, just kind of coordinate. You could talk to your neighbor about this calculation, not about the World Series last night. Anyway, yeah, always in class, you sit with somebody that you know, make friends with somebody, and find a study partner. Start crushing my exams. I can hardly believe it. Another month. And then bang. All right, 30 seconds. Twenty seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, good. You guys did good. Most of you, 94% got it right. 600 nanometers. If you didn't get it right, and actually, even if you did get it right, let's just walk through it. Here we go. There's your equation. And so if you're on exam 4, I might give you something like this in the matching if I wanted you to make a calculation. I'm not saying it's all going to be on exam, but if it is, it might show up like this on the first 4 or 5 questions. Now, if you're doing 5,000 Kelvin, just dunk that into the denominator. Now, look what we got here. Look at that numerator and denominator. Look at them carefully. You see anything nice? Definitely. You can cancel kelvins. So get rid of those babies. All right, but you can't cancel in nanometers, but that's good because you want, wavelength's going to be nanometers or, micrometers or millimeters. Infrared is measured in millimeters a lot of times. Microwave. Your cell phone, what's the frequency for cell phones is in the gigahertz. So it's 10 to the minus 9. So you're talking a few millimeters for cell phones for the wavelength. Anyways, so you cancel kelvins, you get a bunch of nanometers. And then you know what I do? I cancel out 3 zeros top and bottom. Why not? So here's an even cinchier calculation to make. So if you're doing it on pencil and paper, yeah, you can do this one. 3,000 divided by 5. And so, yeah, your answer is then 600 nanometers. And hey, you guys, that's right on the money. That's in the red end of the Roy G. Biv. Remember, Roy G. Biv, the V of violet goes 400 nanometers or so, and the R of red goes about 700 nanometers. So this is good. This is red. It's a little more orange than H alpha. H alpha is 656. So this is maybe a little more orangey red, but it's definitely, and there it is. It's in the reds. So this diagram, figure 3, is pretty good. Pretty good for government work. And so if you had a cooler temperature, you could, so do the same calculation with 4,000, and you'd see that your peak wavelength is even bigger, all right? And so that Wien's displacement law is something that we use all the time. Now, the way that we use it as an astronomer is this, and go ahead and make a note of this in your notes. What we do in astronomy, we'll measure the wavelength, we'll actually find the wavelength, and from that, compute the temperature of the surface. So we'll look at a star, even if we can't triangulate out by parallax to the distance, we can still figure out the peak color. So we put it in our diffraction grating, measure the V's, measure the I's, measure the B's, measure the G's, the Y's, the O's, and the R's, and maybe some infrareds, and maybe a little bit of ultraviolet. And we figure out where the peak is, and then we say, all right, that's my wavelength. Let me calculate backwards to get capital T, the temperature. And so that's normally what we do. And the reason that we do that is because the Stefan-Boltzmann Law tells me all I need to do is know the temperature, and I can know the absolute luminosity. All right? And this is from chapter 5 as well, Stefan-Boltzmann Law, capital F for flux. Now, we're not talking about the flux capacitor here, but we are talking about watts per square meter. The flux is measured in watts per square meter, or gigawatts per square meter. And we have had a quantity already that we've talked about that's measured in watts per square meter, the solar constant. 1367 watts per square meter. That's the amount of energy per square meter hitting the Earth from the SUN. Remember we talked about that? And how Mars has a slightly different one that's down at 800 or something. Okay, the solar console. So yeah, so if you know the surface temperature, we can't even, we might not be able to parallax out and we might not even know its distance, but for darn sure we know its temperature, its color, and its luminosity per square meter. Now here are the units. So if you have a red star or any star, every square meter has the same number of joules per second burning off the center. Now, I'm going to tell you something about this. There's an enormous amount of trig and calculus behind this formula, so we're not going to derive the formula. I wouldn't even want Miss Courtney to try it. I mean, only if I wanted to, completely burn her brain to a crisp. But maybe a grad student, it would be challenging for a grad student too, to figure out Stefan-Boltzmann. But it's a fairly simple law. The constant sigma, that's a constant of nature, 5.67 times 10 to the minus 8 watts per square meter per Kelvin to the fourth. And then you multiply it by the fourth power of a temperature. So if we were doing 5,000 again, we'd go 5,000 to the fourth power. By the way, you better figure out how to do fourth powers in your calculator, because next Tuesday I'll probably give you some clicking calculations with Stefan-Boltzmann. Oh, by the way, you're going to have some homework this weekend, and I know you love homework. It's so much fun. I heard somebody go, yeah. And I'm going to give you some Stefan-Boltzmann calculation practice and a little bit of Wien's displacement law calculation practice, just so you can try it out. I'll give you some cinchy ones, and you'll answer Wien's displacement law. I might give you a wavelength, you calculate a temperature. I might give you a temperature, you calculate a wavelength. Do it both ways. And then I might give you a temperature, and you calculate the flux and see if the flux capacitor will flux. So this same law applies to any color. All right. So the Stefan-Boltzmann law is really nice because it's a way for us to know the intrinsic luminosity of a star. And then if we measure its apparent luminosity, we can figure out the distance to the star. And so that way, we can, even if we can't get parallax, we can still get the distance. It's pretty slick, right? And the whole thing is just figuring out peak wavelength. So let's review the logic of Wien's law and Boltzmann's law. All right? So here we go, surface temperature logic. All right, this is what you would do if you're at the observatory and you gotta figure out the luminosity. How many joules per second for every square meter of this star that you're, looking at, you're eyeballing. Whether it's Albireo or any other star, here's what you do. Okay, you use a diffraction grating. You split the starlight up into its rainbow. So you'll see some Roy G. Biv for most stars. A red star is not going to have much other than R and O, but you'll be able to see a little bit of weak violet and blue and indigo and maybe a little green, but mostly ROY if it's a red star. All right, so you do that and you measure the intensity of each color. Okay? So, or you could, even go in by wavelength, measure the intensity of 400 to 450. Measure the intensity of 450 to 500. Measure the intensity of 500 to 550. You can, with certain light meters, you can measure really precisely for every 10 nanometers of wavelength. So you do all that and you find which one is the brightest. Right? For the sun, it's kind of yellowish green. And why do we know that? Because the temperature of the sun is 5,800. So that's pretty close to this top one here. It's a 6,000 Kelvin curve, and the sun is going to be just dipped a little bit below that. So anyways, you figure out which is your peak color, and then from that you use Wien's law to get the surface temperature. All right? Now we used temperature to get a wavelength. This is the reverse psychology to that. You use a color wavelength to get a temperature. All right? Once you get the surface temperature, you can figure out the luminosity using the Stefan-Boltzmann Law to get F, the flux. All right? And it's very, very handy. And that is one of the ways that we know that that star, the orange one is giants and in Albireo, and the blue one is a dwarf. We know that because we know how bright they are to us and how bright intrinsically they are because we know the surface temperature. The color of those stars, blue, the color of the other star, orange, gives us a temperature. Stefan-Boltzmann gives us the absolute intrinsic luminosity. Then we measure the apparent luminosity here on Earth, and we do a little bit of logarithms, stuff like that, and figure out the distance and how big it is. And then we know it's a dwarf, or we know it's a giant. So it's pretty cool. It's very handy. And one of the nice things about the color, the temperature, is that you can usually measure it even if you can't triangulate a parallax distance. So we can see stuff in other galaxies. And actually, when we look at supernovas detonating, over the course of a week, 2 weeks, as the light dims out from the big explosion, we're looking at that. That's in another galaxy. But yeah, we do this. We try to get the same techniques. We look at those stars and figure out the surface brightness and stuff like that. All right. Now, we're going to have a big reading assignment due Tuesday. I'll try to get it ready tonight. By lunchtime tomorrow latest, you're dismissed. Come on up to the front if you want to get Exam X printout or Exam 3. We got them up here if you've been slacking. Otherwise, I'll see you guys next week.